The main topic of our presentation is about investigation of changing of center of gravity in quadrature maneuvers. For this reason, we designed a full quadrature dynamics simulator. We named it to Quadsim. So please follow us with our Quadsim. For modeling the quadrature, we need two kinds of coordinate system. It is a fixed coordinate system and it is a rotating coordinate system. Our quadrature can be displayed here with four motors. The length of each motor to the center of gravity of quadrature can be displayed by L, and the center of gravity vector can be displayed with three kind of value for each one: x sub g, y sub g, and z sub g. Drive a rotation matrix can change the rotating coordinates to fixed coordinate systems. In xy plane, we have also quadrature with four motors. The coordinate of every motor can be displayed. For example, for number 1 is L for x direction, 0 for y direction, and 0 for z direction too. The first page of Quadsim model in simulated environment can be displayed here. We have some blocks. For example, this one, this one, this one, this one, and this one. We'll explain more in future slides. The first one is thrust adjusting. If you click, for example, in number 1, you can change the value of the thrust forces. You can adjust the thrust value. For slider adjusting, you can change, for example, the mass of slider, the center of gravity in each directional for slider y z direction, and also you can change the animation of our quadrature. For example, if you want to have small quadrature, you can change it to 1, and so you have a smaller quadrature. It's only for animation. In Quadsim main part, you have 1, 2, 3 forces in translational and 1, 2, 3 torques in rotational. External forces applied at x direction can be displayed here, and the Simulink blocks can be displayed here too. M is whole mass of quadrature. As you know, g is gravity acceleration, and sinus theta. Theta is angle of origin of quadrature about y-axis. C sub d1 is drag coefficient about x-axis, and you demonstrate velocity of origin of quadrature along x-axis. But about the external forces applied at y direction, you can see this formula and the block system in Simulink. Phi, sinus phi. Phi is angle of origin of quadrature about x-axis, and v is velocity of origin of quadrature along y-axis too. But what about z direction? At z direction, you can see this formula. But what about w? W is velocity of origin of quadrature along z-axis. You can see for types of c sub 1 omega sub 1 squared. Omega sub I is angular velocity of each motor. Motor number I of quadrature about z-axis. But what about external torques applied about x direction? You can see this formula and the blocks in Simulink. What about tau? Tau is the torque produced by force of motor of quadrature, and p is angular velocity of origin of quadrature about x-axis. But what about y direction? The external torques applied about y direction. You can see, and about z direction, you can the formula and blocks in Simulink. But what about moments produced by the effect of slider changing? As you know, when the slider is changed, the mass of the slider can produce a torque by the value of forces of each motor. As you can see, the arm of this torque can be displayed here. The vector C sub motor number I minus the coordinate sub G. G demonstrates for center of gravity, and tau is external multiplication multiplied here. But what about the moments produced by slider changing? As you know, the slider can produce a moment. We name it with tau. Tau for every motor has a vector with three values: tau sub ix, tau sub iy, and tau sub iz2. But what about the function can be displayed here? The function is written in MATLAB editor, and you can see the external multiply. But what about the Quadsim equations and 6 diagram of freedom? As you see, we have differential and we split the algebraic equations. In differential parts, you can see u is x dot, v is y dot, w is z dot, p is phi dot, q is theta dot, and r is sin 2. And you can see the blocks in Simulink with initial conditions can be displayed inside area of this integral block. The equation in x direction, you can see this formula with the Simulink. Y direction is here with Simulink, z direction is here with Simulink. About x direction and about y direction and about z direction. But what about the modified position of center of gravity and value of moment of inertia? When we have the slider mass, the center of gravity can be changed to these new and modified equations, and the moment of inertia have this kind of behavior too, and the blocks for our changing is displayed here. But the transforming from rotating reference to fixed frame reference frame can be displayed here, and the workspace values are transformed to workspace from Simulink with this kind of blocks. But what about our animation and simulation, this Quadrotor and the thrust forces? But this is a hovering. Please see it. I stable the Quadrotor with its weight, and you can see we don't have any changing in our motion. But when we increase the thrust forces, we can see the upping and the going down. For example, when the decrease the thrust forces, we go down and go up. But when we change the thrust forces in this shape, we have rotating. But it is, for example, in hovering, we can't rotate in hovering, and we can rotate by going up or going down. What about this shape of changing of thrust forces? We move right or left. Please see it in this animation. You can see when we change the thrust forces with this shape, we can move right or move left. What about the center of gravity, the main reason for this presentation? When we have, for example, this slider with a very small mass, you can see a slider changing on x-axis. The slider drives on x-axis, and you can see the simulation here. The slider changing on x-axis. But about y, When slider changes on y-axis, it dives on y-axis. You can see the change of center of gravity and change of the quadrature. But what about the xy? When slider, for example, change on xy plane, you can see we have only in xy plane movement. But what about the rotating with slider changing? It is very amazing. Please see it going up with rotating and changing sliding on x-axis. It means that we go up but slider is changed and dives on x-axis. But what about this? We go up with rotating on y-axis and we can see this change on xy plane. It is very amazing with changing slider on xy plane. And what about the move right or move left? Please remember it in previous slide, but we didn't have any slider changing, but now we have a slider. It is very amazing. Moving right with changing slider on x-axis. On y-axis, and slider dives on xy plane when it rotates, move right. It's more amazing if, for example, we change the mass of our slider 5 times heavier. It is very sensational. Moving right, we change the slider on xy plane with 5 times heavier in mass of slider. But what about reciprocating trajectory? We define the trajectory with this kind of signal generator in Simulink, and we can see the result of this changing. Please see it. The slider changes in this direction, and after that it changes its direction to another, vice versa, and so the conductor can change its trajectory and settle on origin point. It's a reciprocating maneuver. Okay, what about the initial conditions introduced as Simulink environment? We did it in callbacks in model properties in Simulink. What about the conclusion? We propose that the change of center of gravity can change the trajectory, and also change of center of gravity can compensate the trajectory if we can design a robust controller. But we have some challenges. The first one is the aerodynamics coefficient. The second is a slider changing device fabrication. It is more important. And the last one, and the challengeable one, is control policy due to nonlinearity behavior. And for this reason, we propose the using fuzzy with reinforcement learning. This kind of controller was produced in Stanford University with group of Professor Andrew and G in helicopter. And for this reason, we suggest the fuzzy reinforcement learning for control policy for this kind of nonlinearity dynamics in our quadrotor. And finally, thanks for your attention. Thank you very much.